Look at electromagnetic radiation, and I wanted to expand on this because I think when we look at heat transfer, radiant heat transfer is the most difficult thing to understand. So I want to spend a few moments on it. So we've looked at conduction, convection, radiation, mass transport, and heat generation. So here we're focusing sort of on infrared, but I wanted to go over electromagnetic radiation generally and hopefully talk about a couple of interesting things. And you've had this in physics and somewhere across your educational path, but I did want to present it a bit more. So what you have at the top is there's a, and that's what you're looking at here with the red being the electrical, just to help you out here. So these are just some factoids related to light and then over to sunlight too, since that's a big issue for us. And so as I mentioned, photons have no mass, which means they can travel at the speed of light, or the speed of electromagnetic radiation. So as things get, well, the speed that something can travel is constrained by its mass. So only things that have no mass can go at the speed of light. And that's Einstein's special relativity principles that talk about mass increases, velocity increases. And they're a measure of energy, and we'll look at the formula for that. So the energy of a photon, a chunk of electromagnetic radiation, is a function of its frequency, and high frequencies have high energy. That's all there is to it. We'll look at the math on there, but that's all there is to it. Multiply it by Planck's constant, and you have an energy function. And it has these three properties: frequency, wavelength, which are unrelated, and speed. And the speed for massless electromagnetic radiation is the speed of light, or c, in that E equals mc squared equation that you've always enjoyed. And that's the basics of it. We'll look a little bit at the math and kind of delve into the concepts a little bit. And then bouncing over to sunlight, which is important for many parts of the heat transfer issue. At the Earth's surface, about half of the light energy comes in as infrared. It's actually more than that. It's up to 55% comes in as infrared. 40% is visible light. More than that, actually, I think it's about 42%. And 3 to 5% is ultraviolet. So that's what is hitting the Earth. And, you know, this term albedo I'm not talking about, which is shown with the Greek letter alpha, because you see that a lot in architecture and earth science, and I don't want to confuse it, so that's why I'm not using that term, and I just mention it because when you look at environmental issues, often you'll see that term used, and it's like reflectivity. Okay, so that's the basic gist. So let's look at a couple of equations here. This is a real simple equation. So all it's saying is A is F, in this case frequency, and sometimes that's shown with the Greek letter we'll talk about later. Times is constant equals energy. Really simple. And that's high energy photons are high frequency. You can think microwaves if you like, X-rays, that sort of thing. They're zapping you and they can heat things up and do all kinds of stuff. And at the bottom here you see spectrum. I'll show it in a couple different ways, but that's all there is to the energy component of electromagnetic radiation. Function of frequency, nothing else. Very few times you would encounter a relationship that simple. And here we're looking at the spectrum, and this is just kind of giggles. So we're looking at frequency, and things that have higher frequency have more energy, as we discussed. And if they're going at the speed of light, the speed of electromagnetic propagation, more specifically, there's a relationship between the frequency and the wavelength that is equal to this. Okay, I've got a couple forms of this. So if you look at this one here, speed of light, c, equals the frequency times the wavelength. Well, it's a simple relationship, and here's some algebraic manipulations, and even this sort of algebraic triangle you may have seen when you studied Ohm's law. So I can calculate frequency as the speed of light, say, divided by the wavelength, and the wavelength is the speed of light divided by the frequency. So what this means, I mean, the math is trivial, but what it means is if something has high frequency, it has short wavelength. And if you look at the first equation, you can see it. There's a high F value, lambda has to be small. That's all there is to it. And velocity of speed of light, 3 times 10 to the 8th meters per second. And okay. And here's just another version of these these calculations. And here I'm showing you that this is a value, or a letter sometimes reserved for frequency. I'm going to use the letter F, and lambda is right here for the wavelength is commonly used as well. So it's the same equation that you saw before, just with a little Greek intruded, and here you have Planck's constant. So it's the same two equations. So they're really simple and powerful. And what I'm hoping is this helps you, drive home these concepts and what's going on with heat radiation, because that's sort of foundational stuff. I just thought this would be a good look at. So here we're looking at a kettle with hot water being poured into a mug, and we're looking at an infrared image. So the infrared, the emitted infrared, is very bright where the hot liquid is, and it's less bright where it's not. So you see it's hottest where it's in air. There's nothing blocking the infrared, so there's no pot or mug that blocks it. And this is available on Play-Doh too, by the way, this PowerPoint. Now, this is what we looked at before, and it's very dizzying for the eyes. But I wanted to point out just two things that you might find interesting. One is, below here is the frequency of light. So visible light is 0.4 to 0.7. So let me annotate this slightly. So here's visible light right here. Okay, that's the spectrum. So if we go up to, and I'm interested in looking at aluminum. That's what I'm interested in. So this is visible light here, all this visible light. So we can draw a little box around it. Okay, so that's visible light, visible light, visible light. And here's, if you see white paints, let me switch this over. And here's white paint right here. So in the visible spectrum, white paint looks like this. It's pretty flat, that's why it's white. And snow, here's snow right here. So snow is white. But now when you look at the infrared, which is over here, and there's different levels of infrared. It goes actually quite further than how you define it. There's near infrared, which is just above in terms of wavelength, below in frequency, visible light. But here's what I wanted to point out: aluminum. Aluminum is really a neat material because look at how it's quite flat. This is here we're looking at reflectivity. So if something is opaque, it has high reflectivity, it means it has very low absorptivity. So aluminum is really, really, really good at reflecting infrared heat. Blocking it, we'll see. So that's a good way to keep things cool. And anyway, this gets really busy otherwise, but you can look at this. Like there's Caucasian skin, you see right here. And so anyway, the only takeaway here I wanted you to get was aluminum and how aluminum behaves really well at infrared, or high reflectivity, whereas white paint starts falling off. Okay. So does white paint absorb more infrared than black paint? No. So unfortunately, I don't have black paint on here. Black paint is still going to absorb. Well, yeah. Oh, I'm sorry. I'm wrong. I'm bad. Okay. Black paint. So black paint, this is a really good one to look at too. Really low reflectivity, meaning high absorptivity into the infrared. So black paint does absorb more infrared than white paint. So white paint is up here, but it's still much higher than black paint as far as absorptivity. Okay, so there's a lot on this graph, and I didn't want to overwhelm you. Really what I was trying to point out was aluminum. Okay, I wanted to move into something else, namely propagation. So what we looked at here was we noted that electromagnetic radiation, which visible light is and infrared is massless. It goes at the speed of the light. It's a constant because it has no mass. It's pure energy. It has a discrete length called a photon. Its frequency is connected with its energy, and it behaves differently. So we respond to infrared and electromagnetic radiation. We see visible light, and these are physiological issues. They're not constrained by physics. So you could see microwaves, you could see radio waves of different sorts, but you don't. Okay, but we are keen to look at infrared. And here, though, I wanted to look at things more generally, just because it's the world around you. So my hope is that as you walk around and think about green leaves and listen to the radio and things like that, you can get some ideas. So, for example, with green leaves, as you know, they reflect green light. And if they reflect green light, it means they don't absorb green light. They don't absorb green light, but they do absorb red and blue. So if I were to chart the absorptivity of a green leaf, it would be very low in the middle spectrum, the green spectrum, and higher at the other colors and into infrared. So, and there's a lot there that I said. It's you kind of have to process this. But here we're looking at what happens in our atmosphere when it gets irradiated by electromagnetic radiation. Okay, so high frequencies go right through our atmosphere. And I have a little article on my blog, and I can put it elsewhere, about sky color. And actually, it's in the reading in the book too. Sky color and why the sky on the Earth looks different than the sky on Mars, and these sort of things, which we don't need to talk about now. But it's all interesting because you look at the sky every day and you're wondering what's going on. Why is the sun yellow? All these things. These are all answered in some writing I've done. But here we're looking at lower frequencies, radio waves. So you have heard radio stations go on and off the air. You could hear them at night, and then you couldn't hear them in the day if they were far away. And there's sort of roughly two domains of radio waves. There's ones that pass through this layer of the atmosphere called the ionosphere, and there's ones that get refracted by it. And you can see the orange dash line is refracted. It's bent by the ionosphere, and as opposed to going straight through it like light. And I think this is really interesting. And actually, there's just all these really neat practical applications to this. So what happens in the ionosphere is you have ionized layers of molecules. They have charges to them. The molecules up there are close to the exosphere. They're close to outer space, and the sun is bombarding them. And when it bombards them, it kicks electrons out, and it makes charged particles. So you've got this cloud of charged particles way up there. And the density is so low, they don't recombine easily. But when the sun goes away, they recombine. So you get the ionosphere becomes thick during daylight and thin during nighttime. And when it's thick, it absorbs radio, or we'll say short waves, medium radio waves, say from, we'll say 15 megahertz down, okay, generally. Say maybe 20 megahertz down. They get absorbed or reflected. So you get this certain frequency called maximum usable frequency, where you're right at the cusp between when a radio wave would go through the ionosphere and when it would bend. And that's sort of the orange one's kind of showing that. It's getting almost all the way through the ionosphere, and then it bends back to Earth. That's actually the optimal frequency to use for long-range communication. If it's lower than that, the ionosphere is like a sponge and absorbs it. If it's higher than that, it goes right through the ionosphere. So the frequency at which radio waves bounce off the ionosphere changes as a function of the time. So in the middle of the day, it's going to be different than at night. And what happens with an AM radio station far away is during the day, the ionosphere is very strong and it absorbs the radio wave. Okay, but at night, when this ionospheric layer is thinner, less dense, it reflects. And it reflects it efficiently. And actually, there's several layers to the ionosphere. There's a D, E, and F layer, an F1 and F2 layer, and we'll look at that in the next slide briefly. So there's a little bit more to it than a single layer, and these come and go. They're different heights. When we had the partial solar eclipse, I listened with my radio to changes in the ionosphere, plotting noise levels, because when the molecules recombine, they generate noise. When the electron enters the orbital, you get a photon generated, and you can hear that noise. So I think that's interesting just because if you listen to AM or FM radio, you've seen this. FM radio, for the most part, does not go through the ionosphere. Or it does go through the ionosphere. It only works by ground wave, like shown with the blue. And that's the same with cell phones, all that sort of thing. Now, you can get these interesting effects whereby radiation will get trapped between the two layers of the ionosphere and go very, very far, called ducted path. And there's all these other cool things. Like I've bounced signals off of the Aurora Borealis, and people sound like Donald Duck. So you can bounce radio waves that would normally go through the ionosphere when you have northern lights, and it will reflect back down to Earth. And the same is true with meteors too. So if you have a meteor shower, there's an ionized trail behind the meteor, as it goes through our ionosphere that you can bounce radio signals off of. So interesting stuff. And it's anyway, you get this ducted mode, and if you're interested, we can talk to you about that more. But you can get you can get long transmissions of frequencies that would normally cut right through the ionosphere through these ducted modes. Okay, well that's really what I wanted to go over. I think this is interesting in a lot of ways because like you can bounce signals off the moon. You can and these the ionosphere actually has kind of clouds of different density that move through the ionosphere, and they cause focusing and defocusing of radio waves. So you get this it's called scintillation, and you can hear it. Well, kind of hear it. It's like 15 minutes. It's a kind of a gradual thing. But when you bounce signals off the moon wobbles a little bit, called libration, and you can hear that. You hear like a different intensity, and you get Doppler shift and all kinds of neat things that you can. So you can interact with things that you can't see with electromagnetic radiation, and most notably with X-rays. So you can interact with the bones in your body with X-rays, which you can't with visible light because you can't get through to the bones. So this is fascinating stuff. What this means is infrared just happens to be a frequency that behaves in a certain way, just like visible light, and they're affected by charged fields. They're affected by even gravity, right? If you know about gravity distortions, and so these massless photons are really fascinating things. For us, it lets us see things and it lets us feel warmth, and those are the two things